Hey everyone, and welcome back to This Explainer. Okay, today we're going on a totally fascinating journey. We're going to transition from the macroscopic world, the things we can literally see and touch every single day, down into the invisible, microscopic rules of chemistry that actually govern our entire reality. So let's just dive right in and uncover the unseen reality of matter.
Now, right off the bat, I want to challenge your basic assumptions about the physical world. Just take a second. Think about the stuff you interact with daily. The light beaming from your computer screen, the heat radiating from your coffee cup, or even, that feeling of happiness when you run into an old friend. Our light and emotions matter. I mean, they're super real to us. We completely sense them, but do they actually make up the physical fabric of our universe? Hold on to that thought for a second.
Here is our roadmap for today. First up, what exactly is matter? Then, when is it not matter? Number 3, the hidden microscopic world. 4, how matter particles behave. And finally, proving gases are matter.
All right, section 1. What exactly is matter? The heavy truth around us.
Okay, so here's the formal textbook definition. Matter is anything that occupies space, has mass, and can be felt by one or more of the 5 senses. Now, I know, that sounds a bit dry, but let's break it down into something a bit more practical. Basically, if something exists in the physical world, it absolutely must have mass. Even if it's incredibly tiny, it's going to have some weight to it. And it must occupy space, meaning it has volume. It physically takes up room on your desk, in your living room, or, up in the atmosphere. To really put this into perspective, matter spans a truly mind-boggling scale. Just look at these examples. Planets and stars? Matter. The tables and chairs we're sitting at? Yep, matter. Plants, animals, the food we eat? All matter. But the crazy thing is, it scales all the way down to a single tiny drop of water, or literally a microscopic particle of sand on a beach. The whole shebang. All of these things, no matter if they're gigantic or incredibly tiny, have mass and take up space.
Moving on to section 2. When is it not matter? The illusion of the senses.
So, if practically everything we bump into is matter, what isn't? Well, let's look at the visual separation we've got here. On the left, we've got clear-cut examples of matter: a pen, a chair, water, clouds. Think about it. If your desk is completely covered in clutter, you literally have to shove things out of the way to put your pen down, right? It demands physical space. But look at the right side. Light, heat, sound, emotions. You can totally feel the heat from a mug of tea, and you definitely see the light from a lamp. But if you shine a light on that same cluttered desk, you don't have to move a book to make room for the light. Heat doesn't have mass, sound doesn't take up volume, and our thoughts and emotions, like happiness or sadness, they don't weigh anything on a scale. They're 100% real, and we experience them, but they are absolutely non-matter.
Which brings us to section 3, the hidden microscopic world. Zooming in to the unseen.
When you look at your digital screen or a wooden desk or even just a plastic pen, it looks perfectly continuous and smooth. But honestly, that's just a trick of distance. It's kind of like a sandy beach. If you look at a beach from super far away, it looks like this continuous, perfectly smooth surface. But the second you walk up and scoop a handful into your palm, you immediately see it's granular. It's made of thousands of individual, tiny grains of sand. Well, guess what? Matter is exactly the same. It is not a continuous block. It's made up of incredibly tiny, individual particles.
To truly wrap our heads around just how microscopic these particles are, let's walk through this absolutely brilliant experiment from our sources. It's a successive dilution of potassium permanganate. Okay, picture this: a beaker with 10 milliliters of completely clear water. We drop in just one single, tiny crystal of potassium permanganate, and boom, it turns the water a deep, vibrant violet pink. Next, we take just 1 milliliter of that pink water and transfer it over to a second beaker that has 9 milliliters of clear water. We repeat this process, taking 1 milliliter from the new mixture and adding it to clear water successively across 5 different beakers.
And this is where it gets wild. Even in that 5th beaker, after being diluted over and over and over again, the water is still pink. I mean, the color definitely gets lighter, sure, but it never actually disappears. So how is this even possible from just one single crystal? Well, it proves that this tiny crystal isn't just one solid chunk. It's actually made of millions upon millions of invisible particles that just keep dividing and spreading out with every single dilution. The sheer quantity of particles hiding inside one tiny speck of matter is just mind-blowing. In fact, if you want a concrete number to attach to this, here it is: 10 to the power of 21. Yeah, that's a 1 followed by 21 zeros.
That is the staggering, literally incomprehensible number of individual particles hiding inside just a single drop of water. Without highly specialized technology, like a scanning tunneling microscope, we're never going to see them with our naked eyes. But they are there, silently building the reality we interact with every day.
All right, Section 4, how matter particles behave. Space, motion, and attraction.
So there are 3 absolutely fundamental characteristics you need to take away from this explainer about how these particles actually behave. Number 1, particles have space between them, which are often called voids. Number 2, they are continuously moving. They're literally never perfectly still. And number 3, they physically attract each other. Let's look at the proof for these because it's super interesting.
Let's tackle that first concept of space with a question. Say you take a glass, you mark it exactly at 50 milliliters of water, and then you dissolve 2 solid grams of salt into it. Why doesn't the water level rise? Think about it. If matter occupies space, adding matter to matter should increase the volume, right? But the water line stays exactly the same. No way, right?
Well, the crucial point here is that the glass doesn't have some hidden compartment, but the water itself actually does. Remember how we said matter is granular? Well, the particles of water have these tiny empty spaces, or voids, between them. When you mix the salt in, the salt particles break down and literally tuck themselves right into these little secret pouches between the water particles. Because they're just filling up the existing empty space, rather than creating new space, the overall water level doesn't rise at all. It's such a perfect demonstration of interparticle space. And actually, this space, combined with the fact that the particles are constantly in motion, is exactly what allows them to mix together so seamlessly.
Okay, moving to Section 5, proving gases are matter. Weighing the invisible. Just think about it for a sec. We are breathing in oxygen and exhaling carbon dioxide right now, right at this very moment. But these gases are completely odorless and totally invisible. We can't touch them like a pen or see them like a glass of water. So, do they genuinely meet the definition of matter? Do they actually have physical weight and occupy physical volume? Let's actually prove that gas has mass. Imagine a super simple balance scale. On both sides, we attach fully inflated balloons. Okay, the scale is perfectly balanced. Now, if we take a pin and pop one of the balloons, letting all that invisible gas escape, what happens? The scale immediately tilts downwards on the side of the inflated balloon. So even though we can't see the air inside, that air clearly has weight. It has mass, and it's literally heavy enough to tip a physical scale. Okay, but what about volume? Does gas actually occupy space? Try this little experiment. Take a glass, stuff a piece of dry cotton all the way into the very bottom of it, and then push the glass directly upside down into a bowl of water. Logically, you'd think water would just rush in and soak the cotton, but it doesn't. The water stops partway up the glass, and the cotton stays perfectly dry. Why? Because that so-called empty glass wasn't actually empty at all. It was completely full of invisible air. And because that trapped air occupies physical space, the water literally cannot enter until you tilt the glass to let the air bubbles escape. So gas takes up space, and gas has mass. Ergo, gas is matter for sure. Real quick before we wrap up, do you remember that rule about particles attracting each other? Well, the force of this attraction varies wildly from one kind of matter to another. This totally explains why you can easily snap a piece of chalk in half with your bare fingers, but if you hit a solid iron nail with a hammer, it's not going to break. The invisible particles in the iron nail have a way stronger force of attraction keeping them locked together than the particles in the chalk. And that brings us to the end of our journey today. From the massive stars in the sky to the invisible air trapped inside a drinking glass, absolutely everything physical is made of trillions of tiny, moving, attracting particles. So, look around your room right now and ask yourself, what invisible matter is interacting with you at this very moment, silently shaping your reality? Pretty wild to think about, right? Keep questioning the world around you. Thanks so much for joining me on this explainer, and I will catch you in the next one.